Hello everyone. On this video we will be looking at geometric applications of cross products. Okay, so first we're going to look at the properties. Okay, so starting off, what if we let A and our B vector represent non-zero vectors in space. Of course, that could be two-dimensional or three-dimensional. And let theta represent the angle between A and B. The angle between our A vector and our B vector. Alright, so first, the cross product of A and B is orthogonal to both A and B. Okay, and remember, orthogonal just means that basically a right angle. Okay, so the magnitude of the cross product of A and B is equal to the absolute value, well, not the absolute value, excuse me, the magnitude of the A vector times the magnitude of the B vector times sine of theta. Okay, so the third geometric property, if the cross product, let me clean that up a little bit, if the cross product of the A and B vector is equal to 0, okay, that's only true if and only if, so if you say that IFF, it just means if and only if, the A vector and the B vector are scalar multiples of each other. Okay, and if that is the case, that of course means they're parallel. And our fourth property the magnitude of the cross product of A and B is actually equal to the area of a parallelogram having A and B as adjacent sides. All right, so those are the four properties we will be going over on this video. All right, so if you are still writing, feel free to press pause. But we're going to go ahead and prove a couple of them, not all of them, but just a few so you can have an idea of how you would prove them. Okay, so the theorem that the cross product of A and B is orthogonal to both the A vector and the B vector. Okay, so we'll go ahead and just prove that really quick. Okay, so if you remember, just a little recap. The dot product of two vectors are orthogonal. So the dot product of two vectors, orthogonal. And really that just means perpendicular. When that dot product is equal to 0. So what we're going to do is we're going to calculate the dot product of this cross product and our vector A. Okay, so the cross product of A and B and the dot product of vector A, that is actually equal to, remember our 2 by 2 matrices. You have A2, A3, B2, B3 times the first component of our vector A minus A1, A3 times B1, B3 times the second component of our A vector plus A1, A2, B1, B2 times the third component of our A vector. All right, so if we do our 2 by 2 matrices, we have our first component times A2, B3. Move that up a little. A2, B3 minus A3, B2. Okay, so we have minus A1, B3. So A1, B3 minus A3, B1. And that's times the second component. Plus, we have A1, B2 minus A2, B1. And that's times our third component. Okay, so if we go ahead and just distribute, put that in there. Actually, this A2 I'll put in front. And this A3 I'll put in front also, just to keep it nice and smooth. So we go ahead and distribute those. We have A1, A2, B3 minus A1, A3, B2. We distribute that one minus A1, A2, B3 plus A2, A3, B1 plus A1, A3, B2 minus A2, A3, B1. Clean that up a little bit. There we go. All right, so now you have A1, A2, B3 minus A1, A2, B3. So those two cancel each other out. We have A1, A3, B2 negative, and that's positive A1, A3, B2. So those two cancel each other out. Okay, so we have A2, A3, B1 minus A2, A3, B1. So those two cancel each other out. So we end up with 0. Okay. So actually it would be the same process with the cross product of A and B and the dot product of B. We'll end up with equal 0. Okay, so we know that the cross product of A and B is orthogonal to both the A vector and B vector. All right, so that was a quick proof there. All right, so if you are still writing, feel free to press pause. Okay, but we're going to go ahead to the next page. All right, so for this quick proof, we'll say if theta is the angle between our A vector and our B vector. Of course, that means so theta is between 0 and pi. Then the length or magnitude of the cross product of A and B is equal to the magnitude of A times the magnitude of B times sine of theta. All right, so we're going to do a quick proof of this one. Okay, so starting with the right, we'll see that the magnitude of A times the magnitude of B times sine of theta, we know that sine squared theta equals 1 minus cosine squared of theta. So if we square root that, you know sine of theta equals the square root of 1 minus cosine squared of theta. You go back to your trig identities. Okay, so that's the magnitude of A times the magnitude of B times the square root of 1 minus cosine squared theta. Okay, so we also know that cosine of theta is equal to the dot product of A and B all over the magnitude of the A vector times the magnitude of the B vector. So we can just go ahead and replace that there. I'm going to move this over a little. Okay, so the magnitude of A times the magnitude of B times the square root of 1 minus the dot product of A and B vector divided by the magnitude of A times the magnitude of B, and that whole thing is squared. All right. So what we're going to do is we're really just going to replace this 1 with the magnitude of A times magnitude of B squared over magnitude of A times magnitude of B squared. Okay, since anything divided by itself is just 1. Okay, so we have, I'll make that a little bit, that should be multiplying, not equal. Okay, so we have the magnitude of A times the magnitude of B vectors squared over the magnitude of A times the magnitude of B vectors squared minus, go ahead and distribute that exponent, the dot product of A and B vectors squared over the magnitude of A times the magnitude of B vector squared. Okay, so 1 minus what we already have. Okay, now I'm going to just separate the numerator and denominator there. So we have magnitude of A times magnitude of B times, we have the magnitude of A, both of those are squared, so we'll just separate those and just make both of those squared, minus the dot product of the A and B vector squared over, since those denominators match, we'll just put those right over there. So we have the magnitude of A actually I'll leave that as squared times the magnitude of B vector, that whole thing squared. Okay, so we can see here that the square and the square root actually cancel each other out. So we have the magnitude of A times magnitude of B over magnitude of A times magnitude of B. So those two cancel out. Okay, so we are left with the magnitude of A squared. That would be the square and square root will actually cancel out for that one. So we're left with the first component squared plus the second component squared plus the third component squared times the magnitude of B squared, so the first component squared, second component squared, plus third component squared, minus the dot product of the A and B vector squared. So that leaves you with first component of A times first component of B, second of A, second of B, third of A, third of B squared. Okay, but after a whole lot of algebraic manipulation, that you are free to do when you multiply these two together and multiply, and then you have a bunch of things canceling out, you will be left with the magnitude of your cross product. All right. Okay, so if you are still writing, feel free to press pause. But we're going to go ahead and move on to our first example. Okay, so for example, we want to show that the cross product of A and B is orthogonal to both the A vector and B vector when A vector is equal to 2, -3, 1, and B vector is equal to 1, -2, 1. All right. So instead of writing the cross product of A and B over and over and over, we'll just let W vector equal our cross product of A and B. Okay, so when we find the cross product of A and B, we have your I, your J, your K. Then you have your A first, so you have 2, -3, 1. Then you have 1, -2, 1. Okay, so we can find our cross product there. Okay, so that is equal to, if we cover up our I, we have -3, 1, -2, 1. So -3, 1, -2, 1. And that's times your I vector. We cross out the J, we have 2, 1, 1, 1. So that's minus 2, 1, 1, 1. That's times the J vector. Plus, we cross out, so cover up the K. We have 2, -3, 1, -2. So 2, -3, 1, -2, and that's times the K unit vector. Okay, so if we go ahead and do our determinant, so we'll move this down here. So this will equal -3 times 1 minus 1 times -2. times the I vector minus 2 times 1 minus 1 times 1 times the j unit vector plus we have 2 times negative 2 minus negative 3 times 1, and that's times the k unit vector. All right, so we go ahead and simplify that. We have negative 3 plus 2 times the I vector minus 2 minus 1 times the j vector plus negative 4 plus 3 times the k vector. Okay, so our cross product, which we'll just call W, our W vector is equal to negative 1i, so that's negative I vector, negative 1 times our j vector, so negative j vector, and negative 1 times k, so negative k vector. Okay, so we know that the dot product of the A and W vector will have to be 0, and the B and W vectors will have to be 0 to show they are orthogonal. Okay, remember we're going to get that so we'll know what we're working with. Okay, we have our A vector and our B vector right up there. Okay, so the dot product of the A vector and our W vector okay, our A vector is 2, negative 3, 1. And it's the dot product of negative 1, negative 1, negative 1 for our W. This is also equal to, let me kind of expand that, negative 1, negative 1, negative 1. There we go. So we can use either one of those, but just choosing to use that. Okay, so that's going to equal 2 times negative 1 plus negative 3 times negative 1 plus 1 times negative 1, okay, which gives us negative 2. Clean that up some. There we go. Negative 2 plus 3 minus 1, which is 0. Okay, so since the dot product is equal to 0, we know that they are orthogonal or perpendicular, however way the assignment calls for it. Now we do the dot product of our B vector and W. Okay, so of course our B vector is 1, negative 2, 1, and that's the dot product, again, of negative 1, negative 1, negative 1. Now let's separate that a little. Okay, so that's going to equal 1 times negative 1 plus negative 2 times negative 1 plus 1 times negative 1. Okay, so you have negative 1 plus 2 minus 1, which again is 0. Okay, so we see now that the cross product of A and B, which was our W, is orthogonal to A and both B. All right, so if you are still writing, feel free to press pause. But we're going to go ahead and go to our next example. All right, so let's say, for example, we want to find the area of the parallelogram with vertices at the points, say point A, that's equal to 5, 2, 0. Say point B is 2, 6, 1. Say point C, move that over a little bit. Point C is equal to 2, 4, 7, and point D is 5, 0, 6. Okay, so to kind of help visualize, I'm going to go ahead and kind of draw a makeshift graph here of our parallelogram. That's our X, Y, and Z. Okay, so for point A, we have 5, 2, 0. So let's say we're going up 5, down the y-axis 2, and we don't go up on the z-axis, so we leave that right here. That's our point A, 5, 2, 0. Okay, so our point B, 2, 6, 1. So let's say X is 2, Y is 6, Z is 1, so we go up. So 2, 6, 1 is about right there. Okay, so for point C, we have 2, 4, 7. Okay, so X is 2, Y is 4, and we go up 7, so that would be about, I'll say right there. Let's see, 2, 4, 7. And point D, 5, 0, 6. So X is 0, X is 5, Y is 0, D is 6. So we go up to about there. Okay, so let's say that what we're looking at, this is a rough sketch. That's our point D, 5, 0, 6. Okay, so it's kind of a rough sketch of what we're working with, but it helps us to visualize. Okay, so the first thing we have to do is we have points, but we have no vertices. We have to actually calculate our vertices. Okay, so for the directed line segment AB, we can create the vertex. Remember the first component of the terminal point minus the first component of the initial point, and we just keep going down. So that's 2 minus 5, then 6 minus 2, and then 1 minus 0. So we end up with negative 3i plus 4j plus k. Okay, so for AB, that's our vector. Now we have A to D. We do the same thing. A to D, so we have 5 minus 5. We have 0 minus 2. We have 6 minus 0. So we end up with 0i minus 2j plus 6k vector. Okay, so now we do the same thing for C to D. That's 2 minus 5, or 5 minus 2. That's 0 minus 4. And that's 6 minus 7. Okay, so that's 3i negative 4j minus k. And we have from point C to B, we have 2 minus 2. We have 6 minus 4. And we have 1 minus 7. Okay, so we have 0i plus 2j minus 6k. Okay, so if you notice, all of your parallels are kind of opposites. But if you look, you notice that point AB, well, the directed line segment AB is parallel to the line segment CD. Okay, AB and CD, they're parallel. And also, the line segment AD is parallel to CB. Okay, so AD and CB are parallel. But to use the formula we need adjacent sides. Okay, there are multiple adjacent sides, but we're going to pick line segment AB and AD because they're adjacent to each other. Are one of the adjacent sides. Okay, you didn't have to pick that one, but that was just the one we picked. You could have picked BC and CD. As long as the sides are adjacent, you're okay. All right. So now we have to find the cross product of these two sides. Okay, and kind of separate that a little. Okay, so the cross product of AB and AD, and if you like, you can make that vertex A, B, C. It doesn't matter. I just left it like this. Okay, that's equal to, then you have the I, the J, the K. You have A to B, which is negative 3, 4, 1. And you have the vertex, the vector A to D, which is 0, negative 2, 6. All right, so we go ahead and calculate to get our 2 by 2 matrices. We cover up the I. We have 4, 1, negative 2, 6. Okay, so 4, 1, negative. Move that over a little bit more. Negative 2, 6. That's times the I vector. Cover up our J. We have negative 3, 1, 0, 6. That's times our J vector. Plus, cover up our K. Negative 3, 4, 0, negative 2. Negative 3, 4, 0, negative 2. And that's times our K vector. Okay, so that's going to equal 4 times 6 is 24, minus 1 times negative 2 is negative 2, times our I vector, minus negative 3 times 6 is 18, or negative 18, and 1 times 0 is 0, so minus 0 times our j vector, plus negative 3 times negative 2 is 6, minus 4 times 0 is 0, times our k vector. So we end up with 26 times the I vector, plus 18 times the j vector, plus 6 times the k vector. All right, so remember, this is the vertex. Keep me say vertex. The vector AB and the cross product to AD. Okay. Now to find the area, we just need the magnitude of that cross product. Okay, so our area is equal to the cross product of the directed line segment AB and the line segment AD, which is equal to the square root of our first component squared plus our second component squared plus our first component squared, which comes out to be the square root of 1036, which simplifies to approximately 32.19. Move that over a little bit. There we go. Okay, and again, if you wanted to make these into just regular vectors, you could have called it vector M, N, O, and P. You could have done that. Okay, so if you are still writing, feel free to press pause. But we're going to go ahead and go to our next page. Okay, which is the triple scalar product. Okay, so the theorem for that. Well, first, we're going to let A vector, B vector, and C vector represent vectors in space. Okay, now for our A vector, which equals 3 components, A1, A2, A3, our B vector, which equals 3 components, B1, B2, and B3, and our C vector, which equals its 3 components, C1, C2, and C3. The volume, which we'll call uppercase V, the volume V of a parallelepiped which is just a prism whose faces are all parallelograms. Okay, so prism whose faces are all parallelograms with vectors A, B, and C as adjacent edges. So the volume is equal to the magnitude of the dot product of the A vector and the cross product of B and C. Okay. So to kind of help you visualize it, okay, so this is vector A, this is vector B, and let's say this is vector C. Okay, so I'm just gonna kind of get that a little bit to kind of connect it there. And let's say this one. This one can kind of straighten up just a little bit here. And try to straighten that out a little. But it's supposed to be perfectly symmetrical, but as you know by now, my drawing is not the greatest. Okay, well, just assume that's a perfectly square parallelepiped. Let's see if I can maybe straighten this up a little bit better. That out a little bit more. There we go. That's a little bit better. Okay, now if all vectors lie on the same plane, then of course your volume, which is that very same formula, is going to equal 0. Because all three are on the same plane, so there's no volume if they're all on the same line. There you go, same line. All right. So hopefully you're not struggling to draw that as much as I was. But mostly it's just for visual confirmation. So if you are still writing, please feel free to press pause. But we're going to go ahead and get started on our example. Okay, so what if we want to find the volume of the parallelepiped? I'm saying that incorrectly, excuse me, because I have no idea how that's supposed to be said. I just kind of guess that's how it's pronounced. Okay, with adjacent edges, P to Q, P to R, and P to S. Okay, that's when P, point P is 301, point Q is negative 125, point R is 5, 1, negative 1, and point S is 0, 4, 2. Okay, 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2 right? Now for the previous example, this is what I was saying earlier. If you wanted to replace these with actual vectors, that's what I'm going to do here. So a vector, I'm going to make that the directed line segment from P to Q. Okay, which is from P to Q, -1 minus 3, 2 minus 0, and 5 minus 1. So you have -4, 2, and 4. Okay, we're going to do the same thing for P to R. From P to R, we have 5 minus 3, 1 minus 0, and -1 minus 1. Leaves us with the vector 2, 1, -2. Okay, so about C vector, that's going to be from P to S, which is going to equal P to S, 0 minus 3, 4 minus 0, and 2 minus 1. Which is equal to -3, 4, 1. Okay, so now we're going to use the formula, the dot product of the A vector and the cross product of B and C. Okay, so I'm going to show you a little bit of a shortcut using this. If you have the dot product of these two, you can actually make your volume equal to, if you put the A in the first row, you have -4, 2, 4, then your B and C in the following rows, 2, 1, -2, -3, 4, and 1. And you do it the exact same way that you did with the cross product with I, J, and K. If you circle the 4, say if you decide to circle the 4, and that disappears, and cover this up, and this disappears, you have 1, -2, 4, and 1. 1, -2, 4, and 1. And it's going to be multiplied by -4. So instead of here, I'm just going to put it on this side. Okay. Minus, now if you cover up the 2, so if you cover up this row and that top row, you have 2, -2, -3, 1. Move that over. 2, -2, -3, 1. Of course, that's multiplied by the 2. Because remember, before it would be I, J, and K. So it's -4, 2, and the last one's going to be multiplied by 4. Okay, so if we cover up the 4 and this one here, we have 2, 1, -3, and 4. 2, 1, -3, and 4. Okay, so now we do the same thing we did before. So we have -4. 1 times 1 is 1. Minus 4 times -2 is -8. Okay. Minus 2 times 2 times 1 is 2. Minus -3 times -2 is +6. Plus 4, 2 times 4 is 8. Minus 1 times -3 is -3. Okay, so we end up with -4 times 9 minus 2 times negative 4 plus 4 times 11. Okay, so we have negative 36 plus 8 plus 44, which is equal to positive 16. Okay, so our volume is equal to 16 cubic feet. Okay, so if you want to figure out the volume, you can actually use this as a shortcut, where your A is here, and then you have your cross product of B and C right up underneath it. All right, so hopefully this made sense, and I will see you on the next video.